All right, we're going to talk specifically about integrals of trigonometric functions. So first, let's talk about the derivatives of those functions. The derivative of sine is cosine, so that means that the antiderivative of cosine would be sine x plus c. The derivative of cosine is negative sine, so that means that the antiderivative of sine would be negative cosine. And finally, the derivative of tangent would be secant squared, so the antiderivative of secant squared would be tangent. So that's the basics, just getting back to the original function from the derivative. I want you to remember what we talked about a couple of lessons ago, where the antiderivative of e to the ax plus b was 1 over a times e to the ax plus b plus c. That's going to come in kind of handy in this next little explanation of what happens when the argument of sine, cosine, or tangent is a little bit more complicated. So the cosine of ax plus b, the antiderivative of that is going to be 1 over a times the sine of ax plus b plus your constant, for the exact same reason. You could go through and take derivatives just to see what I mean by that, but it should be straightforward. Similarly, the antiderivative of sine ax plus b is going to be negative 1 over a times the cosine of ax plus b. And then lastly, the antiderivative of secant squared of ax plus b is going to be 1 over a times the tangent of ax plus b plus a constant. All right, so now let's talk about what happens when I need to find the antiderivative of a power of a trig function. Okay, I know what you're thinking. You might want to take the easy way out, but if you remember, the derivative of sine squared is not cosine squared, so that means you can't go backwards either. You can't say that the antiderivative of cosine squared is sine squared, because it's just simply not. So I need another way to do it. Okay, that's just reiterating that the antiderivative of cosine squared is not sine squared x. So what I need to do is I need to use an identity to change something like cosine squared to something else. If you remember one of the double angle formulas, and these are in your formula chart, so feel free to look that up, one of the identities is that the cosine of 2x is equal to 2 times the cosine squared x minus 1. Okay, well, how does that help me? I can rearrange this, solve for cosine squared instead, and say that 1/2 of the cosine of 2x plus 1/2 would equal cosine squared x. That's just rearranging this identity so that cosine squared is by itself. Okay, well, how does that help me? That helps me because now, instead of taking the antiderivative of cosine squared, which I have no idea how to do, I can take the antiderivative of something that's equivalent to it all the time. That's what an identity is. So instead of taking the antiderivative of cosine squared x, I'm taking the antiderivative of 1/2 cosine 2x plus 1/2, because they are exactly the same thing. So they should have exactly the same antiderivative. So following all the rules that I know, including the ones that I went over in a previous slide, the antiderivative of this is 1/4 times the sine of 2x plus 1/2 x plus c. All right, and that's the antiderivative of cosine squared. And what about sine squared x? Well, if I think back to the same double angle formula, the cosine of 2x is also equal to 1 minus 2 times the sine squared of x. So again, if I solve this for sine squared instead, I get 1/2 minus 1/2 of the cosine of 2x. So now taking the antiderivative of sine squared is the exact same as taking the antiderivative of this 1/2 minus 1/2 cosine 2x, which is 1/2 x minus 1/4 times the sine of 2x plus c. All right. Next slide is hidden. So what about sine cubed? I think this is as far as I'm going to take you, but if I had sine cubed x, how would I do that? Well, I don't have any identities that have sine cubed in them. So what I do is I split it up into sine squared times sine. And I know that sine squared is 1 minus cosine squared. And if I distribute that sine x, this whole thing becomes sine x minus cosine squared x sine x dx. That I can split into two separate integrals. And it's easy to do the first one, but if you look at the second one, that's when you have to look at that and say, oh, I need to use u substitution on that because I have a function and its derivative in the same integral here. So I know what that one's going to be. That one's easy. It's the second one that I need to worry about, so let's worry about it. All right, that's what I had on the last slide. I haven't changed anything. So I'm going to let u, in this second integral here, I'm going to let u equal cosine x. That way du dx is negative sine x, and that means that du is negative sine x dx. And everything that I have is something that can be replaced. So this cosine x is going to be replaced with u. The negative sine x dx is going to be replaced with du. Okay, so if that's what I start with, and I make those substitutions, then my question becomes the antiderivative of sine x, which is the one that I didn't change, plus this one, which looks a lot easier now. It's just the antiderivative of u squared. So my answer is negative cosine x plus 1/3 u cubed plus c. Well, same problem as before. It's got u's in it, and u is a variable I created, so if I make that substitution back of u equals cosine x, then my answer becomes negative cosine x plus 1/3 cosine cubed x plus c. And that is pretty much the most complicated example I could come up with. So if you have any questions on those, please contact me. Otherwise, I will see you tomorrow.